Hello, everybody. This is Dr. Andrew Chrysler again. In the previous video, we looked at the setup for this problem. So now let's solve this problem. So we're going to find the current I2 on this loop. So looking at this current I2, we know that the current is going to be due to an electromotive force. We have two electromotive forces we can consider, the transformer EMF and the motional EMF. Because the loop of wire is moving away from this loop of wire is moving away from the current carrying wire, but we don't have a changing magnetic field, let's use the equation for the motional EMF. Consider this to be 0. And then we'll solve for this by taking the cross of the velocity in the field dotted with DL. So first thing that we're going to do is we're going to convert the magnetic field. Okay. And we're going to convert it to Cartesian coordinates. In this case, we're going to do this using a little bit of a shortcut method by noting that the loop of wire that is here is in the ZY plane only, okay? So this wire with two resistors is in the ZY plane only. So if we look at this wire, the field will be going into it, into the page here, and out of the page on this side. But we can treat this as if we're only in one plane. And so because of that, where the magnetic field is entering the page here, right, this is in the minus X direction. So you can hold up your right hand and determine this using the right hand rule. So because of that, right, all we have to do in this case, like I said, we're going to use a little bit of a shortcut method here, because we're only dealing with this one plane. And so we can easily see that in this case, the phi direction for our problem, the phi direction, which again is determined in the right-hand rule, the phi direction for this loop of wire that's carrying current I2, that's going to be minus X. So we're just going to convert this into Cartesian coordinates like this. And I've also converted R to Y. And that's because in this case, right, the radial distance away from the wire in this problem is in the Y direction. So now we have an expression for B that's in Cartesian coordinates. And we also know from the problem what the velocity is. And this was already given in Cartesian coordinates. So we can find U cross B by setting this up. In the X direction, I take 7.5 times 0 minus 0 times 0. So this is not going to contribute. In the Y direction, I have plus Y, 0 multiplied by this quantity, minus 0 multiplied by this quantity. So again, this is not going to contribute. But then in the Z direction, I have 0 multiplied by 0. So that minus 7.5 multiplied by this quantity. So I'll write this as 7.5 so in total, I now know that the velocity crossed with the magnetic field is in the positive z direction and can be given by this expression. So this is good because, again, let's go back to this. We know we need the VEMF because this is going to lead us to the current that we are trying to find. So their goal is to find this current. And we'll use Ohm's law here, where this is R2, and this is given as the sum of the two resistors. So we're working towards this. We know that we can find that VEMF by performing this closed loop integral, and we've already found the velocity crossed with the field. So this part of the problem we've determined, but now we're not sure about this. And by writing this out and substituting, we have the expression for the velocity crossed with the magnetic field, but we now need to determine and consider what our DL is going to be. So, so let's consider DL. Now, looking at this problem, recall I labeled each of the 4 corners of our loop of wire, and we could find a DL for each segment of the wire. So let's look at this, and from 1 to 4, okay, so from 1 to 4, like this, we can see that this is in the z direction. So for this segment, we have DL is equal to z hat dz. Now, looking at our U cross B, we can see that this segment is going to contribute because the dot product here is going to be non-zero. Now let's consider the next segment of this loop from 4 to 3. And the DL on this segment is in the y direction. So we would have a DL, make this quite clear, as y hat dy. Now, if I take this z hat vector and dot it with this y hat vector, it's going to be equal to 0. So this one does not contribute to this integral. It's going to be 0 valued. How about from 3 to 2? Well, from 3 to 2, again, we're going to be along the z direction. So this is going to contribute. And we will have the same DL, which is z hat dz. And lastly, again, for this from 2 to 1, we can see that this one is also going to be equal to 0 when we take this dot product. So for the path from 2 to 1 will not contribute to the final result. So now that we know which paths contribute to the final result, we can break up our integral. And I will finish showing you the integral in the last video.